In this video, we're going to take a look at an actual slope field. In fact, that's what you can see on your screen right now. That's a slope field that's been generated by software. And I'm just going to show you how we can use this slope field now to sketch solutions to a differential equation. So the differential equation from which this slope field was derived or generated is this. Dy dx is equal to x squared minus y squared, right? So it's not a terribly complicated one, but it's not linear, right? And it's not separable, so this would not be something that we could solve easily, right? But we have software out there that can generate slope fields, and then let's just see how we can utilize this. And what I will do, let's say we have part A. We have a solution that passes through the point or satisfies this condition. Let's say y of negative 2 is equal to 1, right? Let's see if we could, based on the slope field, actually sketch what this solution would look like. So the first thing I would have to do is locate, and let me switch. In fact, let me do here. So let's locate the point negative 2, 1. So that is roughly probably about there. And then if I want to sketch the solution now that satisfies this particular condition, I'm going to start from this point, and then first I'm going to just kind of follow the arrows. They're directing traffic, right? And then I try to extend it as far as possible as I can go, right, based on the grid. And then do the other thing, try to go all the way back, maybe to where things started, maybe down there, right? So, I mean, within, what, 5 seconds, I'm able to sketch the solution to this differential equation without ever having to do an integral or any kind of analytic method, right? But then looking at this picture, there's a lot we can tell. We can tell, for instance, that this solution, whatever its equation, we can see that in the interval x equals negative 3 to positive 3, this function has a relative maximum. Look, I mean, and it looks like it's roughly maybe at x equals negative 1.5 and maybe y equals 1.5 roughly has a relative min, and then it has a relative maximum, and then it has a relative minimum maybe close to x equals 0 and like y equals 1/4. So we could say, for instance, this solution, two very important properties can be observed just by looking at the graph. So it has a relative max approximately at negative 1.5 comma 1.5, and then it has a relative min roughly maybe a little bit past 0. Maybe it's just my sketch isn't that great, but let's say at 0, and then roughly a y value of maybe a third. Yep, 1/3, right? So quite quickly, I mean, we have a very detailed sketch of the solution, and we can start to identify some really key properties. If we wanted to, we could mention concavity. Concave up, actually concave down, sorry, concave up. So there are lots of these properties we can tell just by looking at the sketch. Now let's try a different condition. Let's say part B, another solution that passes through the point y of 0 is equal to 2. So when x is equal to 0, so that's right in the middle here, y is equal to 2, so it's right here. So probably like this point. So going back upwards, it's probably there. And then it comes down, and then it kind of follows the green, right? So that would be a solution that passes through this point. And you can see, again, very different in terms of the graph of this function. This particular function, it only has, again, in this window, right, in this window from x equals -3 to 3, it only has a relative minimum. It doesn't have a relative maximum. So we could say it has a relative min. And so roughly at x equals 1 and maybe y equals 1. So again, this is just a rough estimate, relative min at that particular point, right? But again, quite easily we're able to sketch the solution of this differential equation that satisfies a particular point. All right, let's try one more. So let's say for C, how about we go for the origin, where this one passes through 0, 0. Right, so smack dab in the origin right here. So, what about that one? Well, this one, it kind of flattens out here. So it kind of flattens out a little bit, and then it goes down maybe like that. And then over here, it's like it's gonna follow the green. Everyone's following the leader, which is the green, and my sketch is a little wavy, but yeah, that purple would be the solution that passes through the 0, 0. This one, it doesn't appear to have any relative extrema in this window, right? So no relative min or max, again, in this particular window. Now if I wanted a broader window, then I would have to adjust my settings and whatever software I use to generate this. But I just wanted you to see what a slope field looks like and how it can be used quite easily to create pretty detailed sketches of solution curves without actually knowing what the equation is. And it all stems from the derivative and these little arrows, these little lineal elements that essentially, they're just direct traffic. They tell the solution curves where they go, and the solution curves, they obey. Right? So if life would only work like that, if someone could just tell us where to go and we would always listen, things would probably be a lot better. But anyway, so this is just a short example of how a slope field can be used, and hopefully you found it interesting. And who knows, you'll be able to generate your own solution curves pretty shortly. See you in the next video.